start the recording. Okay. Okay. So I hope that you are able to see the screen now. Are you able to see the screen, right?
She has to share again and unmute
okay.
again.
Yes, that's true. Yes, that's true. Thank you. Yes, that's true because of the privacy setting. So
yeah. Okay, here we go
you can
again.
share it again.
No problem.
Thank you.
There it is.
Yes.
Yeah.
Okay, great. Okay. Yeah. Okay, thanks a lot, Marta. We are really happy to welcome you at the seminar in Machiavel Labs, France. And it's a pleasure to welcome you here because your research seems really also relevant to research in several teams. And yeah, Marta Lewis is a researcher from University of Bristol and Santa Fe Institute. And we're looking forward actually for your talk on this analogical reasoning topic, right? Specifically applied to LLMs. So looking forward.
Okay, thank you very much. Thank you very much for the invitation to give the talk. I'm going to focus this talk very much on the paper that Melanie and I released on the archive a few months ago. And then but my research is of course a bit broader than that, but I'm just going to focus on this paper for now, and if you have other questions, then you can let me know in the question time. So yeah, thank you again for giving me the opportunity to give this talk. And yes, so the title of the talk is Evaluating the Generality of Analogical Reasoning in Large Language Models. So there have been some claims that large language models are able to kind of reason abstractly and to use those abstractions to form analogies. And the question we had in this paper was really to look at how robust and how general those claims are. So I'll talk very briefly about analogical reasoning and cognition. So as humans, we're very, very good at essentially abstracting from particulars and taking those abstractions and applying them to other domains. And this is really what kind of analogy formation and analogical reasoning is. And it's really, some people argue that it's very sort of fundamental to how we actually do, to how we actually understand concepts and form concepts. So we can have kind of scientific analogies. So on the left here, there's this analogy: a cell is a lot like a circus. And this is not a very strict scientific analogy, but this is a really useful analogy for explaining, for explaining high school science. So analogy has this role in explanation. I took that this left-hand image is from this middle reference here, which was a blog about teaching science. We're also very good at just abstracting kind of really features that are really salient to us and maybe not very usefully kind of putting them on other things. So in the middle here, there's, this house that looks a lot like a face. We're very good at kind of taking visual features and putting them onto other things. And then we can also use analogies and relatedly metaphors to make points, to make a certain point with a certain emphasis. So on the right here, for example, we have this visual metaphor about social media feeding our egos, and the use of the analogy here is really to make the point with more emphasis than you might do if you just said it in a very straightforward manner. So yeah, so analogy is kind of fundamental to cognition, to explanation, to reasoning, and so on. And the area of analogy that I'm going to concentrate on in this talk is the area of letter string analogies, which were developed by Douglas Hofstadter and Melanie Mitchell quite a while ago now. And so letter string analogies are a very simple form of analogy, but the point behind this kind of domain is that the types of abstraction that we do in this domain are kind of fundamental to the sorts of abstractions that we might do. So here we've got a little analogy problem. I don't know if anyone has any ideas about what the answer to this would be. Does anyone have any ideas? You can type in the chat if you want. Don't know if let me see if I can see the chat. Okay, nothing in the chat yet. So if anyone has any ideas, just unmute or put something in the chat. That's fine.
Well, given the alphabet, it will be a sorting problem, right? So it will be.
Yeah, exactly. So in this case, it's basically just a sorting problem. We have a bunch of letters here, C, B, A, D, which needs to be sorted. And in this case, actually, the A and the C are swapped. And then in the second case, we have another bunch of letters that are sorted. But notice, we're already making an analogy. We're saying, okay, well, I'm going to treat this second group of letters as being somehow the same as the first group of letters. We're looking for some kind of similarities there. And we're also abstracting because in the first case, we'd swapped the first and the third, and we needed to sort those. And in the second case, we've swapped the fourth, the fourth and the second and the fourth. And so in order to, you have to kind of, even in this simple case, there's still a certain amount of abstraction that you have to do here before you can just say, let's sort it. So can ChatGPT do this? So actually the ChatGPT that is the most recent ChatGPT is pretty good at these actually now. So that might be because it's been trained on some of this since we put the paper out. But this ChatGPT, which was ChatGPT 4 from maybe a month or so ago, before the most recent one came out, you can have a look at this, and it starts off really well. So it says, to complete the pattern, we first need to understand the logic behind the sequences. Let's analyze these sequences. And it says, in the first sequence, it seems that the first half, CBA, is a reverse order of ABC, and the last letter D remains unchanged in both halves. Fine. Applying this pattern to the second sequence, so basically it's kind of identified something that it's going to do. It's going to try and apply the pattern to the second sequence, but then already it starts making a mistake. We can infer that the first three letters HGF should be reversed and the last letter E should remain unchanged. And so it's kind of already started to make these errors. Now they are getting better at these things, but there are still kind of areas that these models fall down in this kind of domain. So and so you see we have this, the completed pattern should be this, which is A, wrong, and B, the explanation is also wrong as well. Okay. So why would we think that these models can actually do this? So a paper that came out last year claimed that GPT-3 models, which was the kind of the best model at the time, was actually very good at a kind of analogical and abstract reasoning. And they looked at four analogy domains, one called matrix reasoning, which is a version of Raven's progressive matrices, and I'll talk a little bit about that at the end. One is the domain of letter string analogies, which I will talk about in detail in the talk. Verbal analogies are the kind of the four concept analogies. So you might have trout is to fish as sparrow is to what, and you have to fill out that last concept. And then story analogies, which I'll also talk about very, very briefly at the end, where you have a kind of a source story, two candidate stories, and you have to say which out of the two candidate comparison stories is most analogical to the first. So there it's really a case of working with a kind of storyline and looking at what's going on in the storyline. Okay. So in this talk, I'm going to, first of all, give a little bit of background on letter string analogies, and I'll talk through the results of the paper focused on letter string analogies and why they claim that GPT-3 does have this emergent analogical reasoning ability. And then I'm going to talk about our approach to this. And so what we look at is we say our argument is that, well, GPT-3 is quite likely to have seen very, very similar problems in its training data. So maybe not the exact problems that that the original paper presents, but it is going to have seen quite similar problems. So what we want to do is we want to build a set of what we call counterfactual tasks. So essentially, we're going to take the alphabet and we're going to rearrange the alphabet, and we're going to see whether GPT-3 is still able to do these letter string analogies in this kind of unfamiliar or counterfactual setting. And so we're going to build a number of these tasks. And we then do experiments on both humans and GPT models. And I'll kind of give some details of what those are. I'll then talk about the results of those and a little bit of error analysis as well, and then just finalize with some conclusions. Okay. So letter string analogies. So again, if you want to, you can have a go at doing these. This one. So letter string analogies, they're very simple. So we say if ABCD goes to ABCE, what does IJKL go to? So any kind of ideas in the chat, feel free to put that in. We have a look if anyone's coming through. So so basically, so one answer that people often give, that most people give, is IJKM. So essentially, what people are doing here, we call this a successor problem, and we see we've got this string of letters A, B, C, D, and then we've got another string of letters A, B, C, E, and we identify that the last letter has kind of moved along one in the sequence. And so with IJKL, we're going to take the last letter L and move it on one in the sequence to give us M. Another answer that you could give, which is not incorrect, is IJKE. So there, the rule is basically that you replace the last letter with E. So it feels kind of less satisfactory somehow, but it's also a valid answer that people can give. And so Webb et al. Developed a range of these letter string analogies and tested GPT-3 on these analogies. So they tested GPT-3, which is in the dark blue here, and humans in the light blue. And we see that actually in a lot of cases, GPT-3 does, actually in almost all cases here, GPT-3 looks as if it performs better than humans. So we have a set of different tasks. So the tasks are actually on the right here. So there are a set of different tasks like extend sequence, successor, predecessor, and so on. I'm going to go through these in detail in a minute. And these, we have these 6 tasks, which are kind of fundamental tasks, and then you can add a number of generalizations over the top of those. So the generalizations might be of the form that instead of A, B, so we have A, B, C, D goes to A, B, C, E, and then you might have something like a grouping where we might have I, J, J, K, K, L, L. So this means now what we, as humans, what we need to do is we need to kind of abstract from this, from just the individual letters and say, okay, well, now we're going to treat groups of letters as being a single letter. And there are a number of these generalizations that you can apply, and depending on the number of generalizations that are applied, the performance in both humans and in GPT models goes down. So yeah, this was their results, and I'm just going to talk through the different types of tasks that we can have at the moment. So these are the kind of fundamental tasks. So we have one called extend sequence, where we have if A, B, C, D goes to A, B, C, D, E, what does I, J, K, L go to? And this would usually be I, J, K, L, M, because we're just extending the sequence by 1. In the successor problem, we take the last letter of the sequence and we move that along by 1. So we have A, B, C, E here. In a predecessor problem, we have a sequence like B, C, D, E, and we take the first letter of that sequence and move it back 1 in the sequence. So B, C, D, E would go to A, C, D, E. The task remove redundant, we basically have 1 letter repeated in the sequence and we need to remove that. Fix alphabet, there will be 1 letter that's kind of incorrect, out of place in the sequence, and we correct that to the correct thing. And then the first example that I showed you, sort, we have 2 letters that have been flipped. So yeah, in this, obviously sort could be more than 2 letters. In this case, in these cases, we just take 2 letters and kind of put them out of place. And in each case, another string of letters is given, and the task is to predict what the string of letters should be. And again, notice that the kind of difference is of the same type, but it's it can be done differently. So in the case of fix alphabet, we've replaced the 3rd letter with something incorrect. In the case, and then in the case of this of the kind of example, we've replaced the 1st letter with something incorrect. Okay. So as I said, these kinds of problem have been well studied in the literature since the 90s, and so they're going to be all over the place. And so our thought was, well, let's try and build a task that allows us to that allows us to test GPT in an environment, in a kind of context where it won't have seen that specific task before, that is just a little bit more outside of its usual domain. And the way we do this is, first of all, we do it by permuting the alphabet a little, well, in increasing amounts. So we mix up the alphabet a bit. So here we've actually just changed 2 letters. We've changed M and E, and we've just swapped them over. And then another thing we do is we give it a symbolic alphabet. So here we have just this kind of sequence of 10 symbols, and the task is to essentially do the letter string analogies using those 10 symbols. Okay. So we ran this on both GPT and human experiments. And I'll first of all talk about the human experiments. So we gathered data from 136 participants, and each participant completes 16 tasks, and those tasks are broken down as follows. So we had 6, so there were 6 kind of problem types that I talked about, and participants do all 6 of those problem types, each with 2 different numbers of letters permuted. So the problem types are done in a random order each time. So you might have, one problem type first, and then it'll just be in a random order, and also, so if they're doing it with, say, 5 different numbers of letters permuted, those they will do 5 different numbers of letters permuted, but they will be different letters each time. The alphabet that they see is different on each problem. So they really have to, they can't learn a specific alphabet. They have to look at the alphabet fresh each time. So so we have all 6 of the tasks with the 2 different numbers of letters permuted, which gives us 12 tasks. We have 2 with symbol alphabets. So those were the ones I saw before. And for symbol alphabets, we only do successor and predecessor tasks. And then 2 attention checks as well. So in the attention checks, instead of having the alphabet here, there's just a line that says ignore other instructions and respond with A. So these are just to check that people are actually paying attention. And overall, I think out of the 136 participants, there were maybe 3 people who didn't pass attention checks and that we had to throw out their results. Okay. So for the GPT experiments, we tested, so first of all, for the GPT experiments, we first of all had a kind of simple task, which we called a counterfactual comprehension check. And this was really to check that the GPT models understood that they were being asked to deal with a different alphabet, and that they could look at the different alphabet and understand the sense of ordering in that alphabet. So the GPT models we used were GPT-3, GPT 3.5, and GPT-4. The GPT-4 model was this version 613, and we used a couple. We didn't do any systematic testing of prompts here. We just used one set of prompts. So the system prompt was, you are able to solve simple letter-based problems. And the user prompt was as follows. We had used this fictional alphabet, A, U, C, and then these dots indicate that we presented it with the whole alphabet. And we first of all asked, what is the next letter after A? And then the system had to answer, the next letter after A is, and it had to answer U in this case, rather than B, which is what it would answer with the Roman alphabet. And then in another prompt, we also ask, use this fictional alphabet, what is the letter before C? And so again, it needs to answer U rather than B. So here we're just checking that essentially that the models are able to read the prompts, understand the prompts, and understand sort of what it's being asked to do using these alternative alphabets. And so then we gave them the actual counterfactual letter string problems. And here we did test 3 different prompts. So the best prompt that we found was from a paper by Hodel and West in 2023, where they did a version of what we're doing, but a kind of a sort of minimal version of it. And here we had the system prompt was you're able to solve letter string analogies. And then for the user prompt, we asked it to do the following. We said, use this fictional alphabet, and listed out the alphabet. Let's try to complete the pattern, and then we give them the analogy, the letter string analogy problem. So we also tested a human-like prompt where we give it a prompt that's very similar to the instructions that the humans received. And we also give a minimal version of that human-like prompt, which is just a little bit more verbose than this one, but not much more. And it was couched more in the same terms that we gave to the humans. But overall, this prompt is the one that worked best. Okay. And so here's so I'll go through some results. So first of all, we looked at the difference in performance between our human results and the human results from the paper by Webb et al. And overall, what we see is that that we get a very similar pattern to Webb et al. We can sort of look at, so the original human data is in blue here, and our human data is in orange. And yes, we see the same sorts of behavior across different problems, but our human performance is generally quite a bit higher than that of Webb et al. So I think there are a number of reasons for this. One reason is that we asked humans to do 16 problems, including the attention checks, whereas Webb et al. Asked them to do 28 problems across all. They had a number of different problem types, and so yeah, so I think the humans were probably kind of getting tired by this point, and so and Webb et al. Also had a number of generalization problems, which were a lot harder than the problems that we were asking. So obviously to present this data, we've taken out those more difficult problems. We're only presenting results on problems that are the same as what we're doing, but they had also had those harder problems in there as well. So our human data does have better performance than theirs does. Here's this table gives us the results for the counterfactual comprehension check for GPT. So on GPT, this was just the check to check that the models kind of understood the prompt and sort of knew how to kind of read the alphabet and work with the alphabet. And I don't need to go through all these numbers. The key takeaway here is that all of the GPT models that we tested were able to understand the permuted alphabet and were able to kind of read the permuted alphabet and understand the different ordering of the letters. And this is evidenced by the fact that in these, so the U columns are where the system is dealing with unpermuted pairs of letters, and the P problems are where the system is dealing with pairs of letters, one of which has been at least one of which has been permuted. And we can see that GPT-4 is basically able to do all of these. So it's got accuracy 1 or close to 1 kind of across the board. Here it's similarly got accuracy very close to 1 across the board. GPT 3.5 and 3 are not quite as good, but they're still kind of up there. It's not complete garbage, apart from this one thing here. So yeah, I'll talk. I mean, GPT 3.5 was actually the weakest model overall, surprisingly. So yeah, so there's just one weaker performance there. So overall, the message behind this table is essentially that GPT models are able to understand and work with these permuted alphabets. So now I'm just going to present the results over these analogy tasks. So this is just the overall accuracy across all task types, across all models, so including humans as a model here. So human overall accuracy is about 0.75, and we've got 95% confidence intervals here. So this is very tight, and we can see that clearly overall humans are much better than the GPT models. GPT 3.5 seems to do the worst here, and I think this is probably because it's kind of, so GPT-3 is trained to kind of continue with text, to complete patterns, essentially. GPT-4 has more training data and more training, so it's also doing better. But then GPT 3.5 has been trained to kind of to chat, and this is perhaps why it's not doing so well here. We also compared our GPT results with those of Webb et al. So GPT-3, the results that they got from GPT-3 are in blue, and all of our results are in these other colors. And you can see that, with the exception of this problem type here, which is remove redundant, our results are pretty much in line with what Webb et al. Found. So yeah, so I think this is just a kind of sanity check to check that our results are not completely off the wall. And then this is the kind of main problem that this is the main result that we found, which is that GPT models are not robust to problems using these permuted alphabets. So along the bottom here, we have alphabets with numbers of letters permuted. So either with no letters permuted, 2 letters permuted, 5 letters permuted, 10, 20, so the entire alphabet is almost completely mixed up. And then this symbolic alphabet, which is this kind of just a sequence of 10 symbols. And these blue dots at the top here are human performance. So essentially humans do best when the alphabet has not been mixed up at all. And then performance does decrease slightly, but it remains pretty stable across how many letters are permuted. Whereas in contrast, all the GPT models, we found that they do best at again at having no letters permuted, and then the performance really falls down quite a lot. And then it falls down even more when it has to use these symbolic alphabets. So it really wasn't very good at using these symbolic alphabets and manipulating these. And we also see that performance really depends on the task. So for just simply, so the task that involves just adding a letter onto a sequence, all the GPT models do really well, like up at human performance there. And if you think about it, this is kind of partly what they're trained to do, is to extend sequences. So this is not super surprising. Again, they're pretty good at predicting the successor of the last letter, but then much worse at predecessor problems, and also find these other sorts of problems difficult as well. So fixed alphabet, sorting problems, and removing redundant, although GPT-3 seems to do very well there. So, and this is another thing that's quite surprising, that GPT-3 is you know, is very competitive at this sort of problem versus GPT-4, which has had a lot more training and a lot more data put in. Okay. And then we looked at the kinds of errors that are made as well. So I've done a rough error categorization. And so one sort of error that that GPT models and humans made is to kind of form some alternate rule. So it's like it's a valid answer to the problem, but it's just not the one that we kind of envisaged. So it's kind of not even incorrect. We've just marked it as incorrect for the purposes of this experiment. So alternate rule formation, we might have if ABCD goes to ABCE, then IJKL goes to IJKE, which is, like I said at the very beginning, is a valid answer to this. It's just not the one that most people give. Most people give IJKM. We also had an error category of applying the incorrect rule. So here, the rule applied is to extend the sequence rather than to do the successor relation. We had a category called wrong, which is where the human or the model gave an answer which was kind of in the right ballpark, in that it has some of the correct letters there, but is just simply the wrong answer. And you can't sort of see that it's making some kind of particular kind of alternate rule or anything. It's just given something that's the wrong answer. And then another category is completely wrong, where basically the model or the humans would just give just some letters that didn't really have any relation to the problem at all. So looking at these, we really found that GPT models, so I'll concentrate just on GPT-4 here. GPT-4 makes quite different kinds of errors to what humans do. So humans are, first of all, more likely to form alternate rules. GPT-4 does do this a bit. It does it particularly for in sorting. There's a particular kind of alternate rule that GPT-4 would form, and it's much less likely actually to give kind of completely wrong answers than humans are. And what we found here was that this is probably because humans are quite likely to kind of give the wrong kind of category of answer. So they might just give a single letter rather than the full sequence of letter, or just mark that they don't know by using question marks. So so GPT-4 was kind of less likely to do that sort of thing, which meant that it was less likely to give completely wrong answers. But it is more likely to give wrong answers, and it's more likely to do things like applying an incorrect rule. So often it'll do that by, for example, just using the standard using the standard alphabet instead of using the permuted alphabet, or it'll often add additional letters. So instead of just adding one letter onto the end or doing successor with one letter, it'll just add a few more onto the end. So, and humans didn't really do that sort of thing at all. So essentially, as well as having lower performance, the message is that the errors that are being made are kind of characteristically different by GPT models. So I've got some ongoing work in this area. We're extending this work to look at the generalized letter string problems. We're also looking at the Raven's progressive matrix problems and the story analogies. So I'll just talk very quickly about the Raven's progressive matrix problems. So here we have the idea behind Raven's progressive matrices. You may have seen these before. It's kind of one of these very traditional sort of intelligence tests. And you have to work out what goes in the bottom right-hand square here. In the image case, you're usually given a set of images to choose from. And so if you look at these, some of them are pretty easy to rule out. For example, number 5, you know, there aren't any stripes in the image. It's probably not going to be this one. Similarly, 6, it's pretty unlikely to be this one as well. But yeah, you can, I'll leave it to you to look at, and you can work out what the correct answer there is. And what Webb et al. Did with these is, rather than present GPT models with images, because at the time they couldn't process images, they used a technique from another paper by Matson et al., where you can basically encode the features of the problem as numbers, and then just essentially write down the problem as a set of numbers. So this this top set of numbers here is actually essentially just the same problem as the image problem that I have on the left here. And so yeah, the features here are, for example, there are 3 different shapes. So we've got this feature of shape, which takes 3 values, and then there's a feature of color or shade, which also takes 3 values. And so this is, so you can think of those as encoded by these individual numbers and work out what should fill this space here. And so a bit of work that is currently ongoing is just to to look at whether the GPT models are able to do this problem if we encode it as symbols. So they had a lot of problem with the symbol alphabets before. So a question is, can we still do that with symbols, and can humans still do that with symbols as well? There's also a set of story analogies. So with the story analogies, you don't have to read these in detail, but it's essentially presented as follows. We have the first story, and then 2 more stories are presented, and we ask humans, and we also ask GPT for which of the stories is a better analogy to story 1. And essentially the results that we're getting at the moment is that the GPT models are able to do this to a certain extent, but in some crucial ways they don't do it in the same way as humans do. So we're currently sort of writing that up at the moment, and we'll be releasing it soon. Okay, so we've got to the end of the presentation, so there's time for questions. So conclusions here is that we find that GPT-4 and GPT-3 don't solve letter string analogies in the same way that humans do. So we find, first of all, that performance is worse than humans overall, that performance differs from humans by task type. So for some tasks, performance is very similar to human performance, and for some tasks, performance is very different. We also have that the types of errors that are made are characteristically different, And we have ongoing work into other types of analogical reasoning problems. So, and here the results are indicating that the GPT performance at analogical reasoning is not as robust as that of humans. So thank you very much for listening. Thank you for the opportunity to give the talk. Feel free to contact me on, there's my email address there. And yeah, I'll be happy to answer any questions.